A modern 3D CAD environment allows an engineer to create a visually flawless, intricate metal engine housing. Every tolerance is specified, every functional surface is mapped out, and in the digital space, the part works perfectly. But if that geometry is sent directly to a manufacturer without accounting for the extreme physics of the factory floor, the design will fail the moment production begins. Die casting forces liquid metal under immense pressure into a cold, rigidly confined steel mold. The thermal and mechanical shock is severe. A geometry optimized strictly for its end use function rather than its manufacturing process traps heat. This causes internal voids, shreds the expensive tool steel, and forces the shop to run cripplingly expensive secondary machining operations just to fix the mistakes. This brings us to the primary commandment of the industry. Don't design castings. Instead, engineers practice simultaneous engineering, the rigorous process of designing the final component and the mold that creates it at the exact same time. Every single surface, radius, and hole on the digital model dictates a physical consequence. It determines exactly how the liquid metal cools and how the massive steel halves of the tool physically separate to release the solid part. A digital design only becomes a physical product when its geometry is explicitly engineered to survive the thermal and mechanical constraints of the die. The first constraint is thermal integrity. The way metal cools dictates its structural viability, making sharp transitions and thick sections highly dangerous in die casting. Engineers often default to adding mass to increase a part's stiffness. In a casting, a thick wall acts as an insulator. It traps heat and induces severe internal stress. This diagram illustrates the problem. In the poor configuration on the left, the sharp internal corner and abrupt section change cause the outer edges to cool rapidly. The thick interior retains heat, creating an isolated hot spot that will solidify last and pull apart internally, leaving structural voids. The immediate geometric correction is shown below it. By adding a simple radius, typically half the thickness of the wall, to the internal corner, heat dissipates more evenly. The ultimate structural goal requires going a step further. The steel better illustration on the right shows a perfectly uniform wall thickness, designated as T, carried completely through the corner. This entirely eliminates the thick thermal mass and prevents the hot spot from forming. If thick sections are banned, engineers must achieve structural stiffness by deploying reinforcing ribs rather than relying on shear mass. The standard procedure is to under-design these ribs initially in the CAD model. This conserves material and allows the manufacturer to test the first sample castings. If the part is too weak, the die maker simply machines away a bit more steel from the tool to make the rib thicker. It is a fast, cheap modification. If a rib is over-designed and needs to be thinned out, the tool maker has to weld new steel back into the mold, an expensive process that significantly reduces the die's lifespan. Mastering the thermal geometric imperative means leveraging shape, specifically uniform walls and calculated ribbing to guarantee structural integrity. Once the metal cools predictably, the next hurdle is kinematics, physically extracting the solid aluminum or zinc part from the rigid steel mold. The most cost-effective manufacturing standard is the simple two-piece die. Two blocks of steel that press together to form the part and pull straight apart in a single vertical motion to release it. The primary enemy of this simple combination is the undercut, any geometric feature that acts as a hook, structurally trapping the finished part inside the steel. This schematic details an external wall undercut. To extract a part with this undesirable profile, the mold requires a mechanically sliding side core indicated by the horizontal arrow. This extra moving block of steel drastically increases the initial tool cost and introduces a major maintenance failure point. By shifting to the desirable geometry on the right, the exterior profile is altered. The functional shelf remains, but the space beneath it is opened up, aligning with the primary vertical draw of the mold and completely eliminating the need for the slide. Horizontal through holes pose a similar challenge. Normally, creating a hole straight through a vertical wall requires a horizontal steel pin to be inserted and retracted before the main die can open. This cross section demonstrates a workaround called kissing course. If the exterior wall slopes sufficiently, the top and bottom halves of the die can be built to extend and meet or kiss exactly at the parting line. Because the steel forming the hole pulls away vertically with the rest of the mold, the process remains a simple two-piece step while still executing complex functional features. Intelligent part geometry engineers away mechanical complexity inside the machine, drastically reducing tool failure points and manufacturing costs. That mechanical simplicity extends to die sinking costs. The exterior shape of the CAD model directly dictates the lifespan of the tool that produces it. If a designer leaves perfectly sharp external corners on the part, the machinist must cut perfectly sharp internal corners into the die block. Under production conditions, those sharp steel edges act as intense points of heat concentration. This diagram illustrates an undesirable sharp internal corner within a die cavity. The localized heat concentration leads to premature thermal fatigue, cracking, and erosion of the tool steel, necessitating expensive repairs. The correction is shown on the right, applying a radius of just 0.25 to 0.40 millimeters to the cavity floor diffuses the thermal stress and preserves the tooling. Beyond preserving the mold, precise geometry eliminates the need for expensive manual post-processing operations like drilling and deburring once the part leaves the machine. This cross section illustrates how a through hole intended for tapping should be modeled. The desirable right-hand image includes a chamfer or countersink core into both sides of the part directly by the mold. Because the dense outer skin of the casting remains intact, the tap cuts a higher quality thread, and the dual chamfers ensure no burrs are pushed out the opposite side, eliminating a manual deburring step entirely. Finally, the design must account for gate and flash removal. Scalloped or intricate outer edges require highly complex trimming dies to shear off excess metal. As seen in this diagram, adding a 1.5 millimeter vertical shoulder between the intricate wall detail and the parting line provides a clean, continuous surface. This allows for a single cheap trimming punch or lathe operation to sever the gates. True design for manufacturability means engineering the CAD file so the physical part emerges from the die completely finished. By applying these geometric rules, a designer consolidates thermodynamics, tool kinematics, and post-processing into a single optimized chip. This opens the door to design for assembly, the integration of disparate materials directly in the mold, achieving mechanical properties that raw casting cannot provide alone. This cross section demonstrates casting a small assembly. A pre-machined steel insert is placed into the die and molten high ductility zinc is injected entirely around its anchoring features, locking the two metals together. This component leverages zinc's ductility. The before forming illustration shows the straight outer walls required to extract the part from the die. The after forming cross section details how those thin walls are physically spun and bent inward after casting, creating a spherical doorknob. This secondary forming process captures an internal void that would be physically impossible to core directly, effectively replacing an entire downstream assembly line with a simple bending operation. Efficient die-cast design is the practice of combining structural requirements, assembly mechanics, and surface finishing into a single multifunctional component. As industry veterans state, die casting design is roughly 80% rigid thermomechanical science and only 20% aesthetic art. By acknowledging the tooling fallacy, by allowing the strict physical constraints of the mold to dictate the digital geometry, engineers guarantee their designs will survive production and perform exactly as intended.